Good morning, students. In my last lecture, I have told you about the equilibrium constant KEQ, and today I am going to tell you about the types of equilibrium constant, means Kp and Kc. You are already familiar with these two terms, Kp and Kc, and I will elaborate a bit about them, and I will tell you about the units also, and I will tell you some of the facts regarding the solid state reactants or the liquid state reactants when they are in contact with the gaseous reactants or the products. And moreover, I will tell you about the effect of mode of representation on the value of KEQ, means how the value of KEQ will change when we change the mode of representation of a chemical reaction. So let's consider a simple reaction of this type, A plus B forming products. It's a reversible reaction. So when we have to represent the equilibrium constant for this reaction, then what we do? The equilibrium constant will be equal to how much? Active mass of the products divided by active mass of the reactants. So this is a simple reaction in which we have taken the stoichiometry as 1. But if the stoichiometry is different, suppose it is 2A plus B forming 3C plus D, then how will the equilibrium constant change? Equilibrium constant will now become, this will be 3, and this is, since the stoichiometry is 1 over here, I am not writing it as 1, and here the stoichiometry is 2, so I will write it as raised to the power 2, the power will be 2 over here since the stoichiometry is 2. Similarly for B, the stoichiometry is 1. So the stoichiometry of B is 1. We can write or we cannot write it because it will be the same. Anything raised to the power 1 is same. So B raised to the power 1 will remain B. So this is our representation for a chemical reaction of this type. The equilibrium constant is given by the ratio of the product of the active masses of the products and the product of the active masses of the reactants. These are our reactants and these are our products. This is an equilibrium reaction. This is a reversible reaction, and this is our value of the equilibrium constant. So now let's come on to our today's lecture. I am going to tell you about the types of the equilibrium constants. So as we are quite familiar with these words, Kp and Kc. So this equilibrium constant, it is of two types, Kc and Kp. We use the Kc term because whenever we are talking about the equilibrium constant in terms of concentration. C represents concentration. So whenever we are talking about the concentration, means moles per liter, molarity. Whenever we are talking about the concentration, we take Kc into consideration, and whenever we are talking in terms of the partial pressures, like we take for the gaseous reactants and the products. So whenever we are talking about the partial pressures, we take Kp into consideration. Okay. So there are two types of equilibrium constants, Kc and Kp. Now I will tell you two main things. Suppose we are taking a reaction in which we are having a solid, any of the reactant or the product is solid. So when we are calculating the Kc, then what we do is that we take the active mass, the active concentration of the solids as unit. Okay. So the first thing to remember is that whenever we are taking solids, whenever there are solids in a chemical reaction, then the solids will have the active concentration, active mass. Active mass is taken as constant and it is taken as unit. This is constant and it is taken as unit 1. Okay. Whenever we are representing it this way, then the active mass of the solids, reactant or the product is taken as unit. And the other thing is that whenever we are taking equilibria in which we are having the liquid and the gaseous phases are present as the reactant or the product, then we always take the liquid's active mass to be constant, because its concentration will not change and it will remain constant. So we take the liquid's active mass Moreover, we talk about Kc means the concentration terms whenever we are dealing with the gaseous and the liquid phases reactions or the ionic equilibria in which we are having the aqueous equilibria. Okay, then we take the terms, we consider the terms Kc. But whenever we are talking about the gaseous reactants of the product, then always we take the partial pressure into consideration as the concentration term, and we take partial pressure as the into consideration. Then only we consider this Kp term. Okay. Now let me explain this to you with some examples. Now let's come over to a simple example of decomposition of calcium carbonate. So how calcium carbonate decomposes? We all know it forms, it's a reversible reaction, and it forms calcium oxide and carbon dioxide. So here this is in the solid state, and this is again solid, and this is our gaseous state. It's a heterogeneous equilibrium. So what we do is, suppose you have to calculate Kc, then what we do is active mass of the product, and active mass of products is how much? CaO and CO2, and active mass of the reactants, that is CaCO2. But as I have told you just now, that the active mass of the solids is taken as constant and is unity. So when it is unity, then obviously we don't have to consider this CaO since it is in the solid state. Neither we will consider CaCO3 because it is again in the solid state. So we will not consider these terms, and in fact we should not write them also. This I have written just for to make it understandable for you. So what we write is only CO2. Okay. So Kc will be equal to only CO2. Active mass of CO2 only. Okay. Since this is constant and is taken as unity. So if we calculate the unit of it, then the unit will be equal to how much? The concentration is always expressed in moles per liter. So Keq will be actually equal to moles. Unit will be equal to moles upon liters. Now let's take Kp into consideration. Kp is actually for the partial pressure. So how we write the partial pressure? We write the partial pressure in this form, P CO2. Again we will consider the partial pressure of CO2 only because solids they don't have, only the gases that exert the partial pressure. So we will consider this thing PCO2 only. Okay. And when we express the units of this, then the CO2 is having the unit of atm. Pressure has atm units, so and there is only one term only, so the unit will be atm. So these are the units in which the equilibrium constant for the concentration and for the partial pressure can be represented. Now let's take another simple example of N2O4 for, decomposing to NO2. N2O4 and NO2. Now first of all, let's balance it. So it will become 2. Okay, I balanced it so as to consider the stoichiometry into consideration, and as it will be shown in the units also. Now this is our gaseous phase and this is also our gaseous state. This means this is a homogeneous equilibrium now. So when we are going to write Kc, we will write it in this form. Kc will be, this was our first example and this is our another example, second example. Okay. So when we write Kc, Kc will be equal to how much? Active mass of the products. We will take stoichiometry into consideration over here. This will become 2. Okay. Divided by the active concentration of the N2O4. N2O4. And since the stoichiometry is 1 over here, so it is 1 over here. Okay. Now let's calculate. First of all, I will write Kp also for that. Kp will be equal to, let me write over here. Kp will be equal to how much? Partial pressure of NO. And how we write partial pressure? In this form. Partial pressure of NO2 raised to the power 2, that's stoichiometry, divided by the partial pressure of the reactant, which is N2O4, raised to the power 1. Okay. So now calculate its units also. So as we are having this thing, so this will be how much? This is NO2 raised to the power 2. And this is in moles per liter. Since we are calculating the Kc, it will be taken as mole. The concentration will be taken as moles per liter. So it will be moles per liter raised to the power 2. Okay? It will be moles per liter raised to the power 2 and divided by what? This will be in moles per liter. Since this stoichiometry is 1. So there will be only 1 moles per liter. Obviously, one of the moles per liter will get cancelled and what remains is moles per liter. So the unit will be how much? Moles per liter. Moles per liter. Okay. Now let's come over to the Kp value. Kp unit. It will be, this is a partial pressure of NO2 raised to the power 2 and so it will be in atmospheres. So atmospheres raised to the power 2 means atmospheres into atmospheres divided by, this will be in atmospheres. So atmospheres ATM. ATM is the unit for the partial pressure. So this will get cancelled out and what remains is atmospheres. So in this way you can calculate the units for Kp and Kc whenever you are given a problem. This was just for that explanation only. Now I will tell you about, I will elaborate this solid and liquid concept more for you by taking another example. This time I am taking an example of a physical equilibria. Means physical equilibria, I have taken example of H2O liquid and ice in equilibrium. So this is an example of physical equilibria because this is not an example of chemical equilibria since we are considering the change of state only. So it is an example of physical equilibrium. Now I will take up the example of a physical equilibrium, H2O changing, liquid changing to the H2O gas. Okay, let me rub it. Now let's take a simple physical equilibrium. Means there is a change of state. H2O liquid means water is in equilibrium with H2O gas means water vapor. So in this case when we have to express Kc, then what we do is that we have to consider the active mass of the liquid here will be taken as unity because whenever we are taking the liquid and the gaseous equilibria into consideration means heterogeneous equilibria in the physical equilibria, then again the at equilibrium the concentration of the liquid is taken as unity. So when we express Kc over here, then we write it as Kc will be equal to active mass of the product only and it is this active mass of the product only and this is expressed in moles per liter because the active mass of reactant is considered as unity. So we will write it in this form. Okay. Similarly, Kp will be, we will be writing in this form. Kp will be equal to how much? Partial pressure of H2 and that will be atmospheres. So in this way we will write the units for Kp and Kc. Whenever we are having a heterogeneous equilibria in which we are having the liquid state and the gaseous state, then the liquid state concentration is taken as unity. Now I will tell you about the equilibria which is set up in when we are using the when we are having the aqueous phases into consideration. So now let's consider another example. So this is a simple equilibria, ionic equilibria it is there, and here we are having the copper in the solid state. This is in the solid state. This is our aqueous phase, okay? This is our aqueous phase. And here the Ag is also in the solid state and this is our aqueous state. And this is our. solid state. So here how do we calculate Kp and Kc? We will see over here. Okay. For Kc, what we do is product of the active mass of the product will come over this side. So it will be Cu plus plus. And since this is in solid state, okay, this is in solid state, so this is taken as constant and it is taken as unity. So we will ignore it and we will not write it over here. And divided by, here also just have a look at the reactants. This is in solid state and this is our aqueous phase. So we will take aqueous phase into consideration and we will keep this one as constant again. So what we get is Ag plus, since the stoichiometry is 2 over here, since the stoichiometry is 2, so what we have is that it will be Ag plus raised to the power 2. So let's calculate the units over here. What will be the units? This will be in moles per liter. So it will be moles per liter divided by Ag plus, this again will be in moles per liter, but now it will be raised to the power 2. Okay. So 1 of the moles per liter will get cancelled with 1 of the moles per liter of the denominator and 1 moles per liter will remain in the denominator. Okay. This is 1 and this is 2. So 1 will remain in the denominator. So what we get is moles per liter raised to the power minus 1. Hope you understand this thing. Okay, this will be moles per liter raised to the power 1. But if we calculate Kp over here, look, one very important thing I am going to tell you now. If you look at the Kp over here, Kp is not defined here. Why? Because not a single reactant or a product is in the gaseous state. Okay. There is no reactant or the product which is in gaseous state. So Kp is not defined over here. Just remember this thing, that Kp is not defined over here. Why? Because none of a single reactant or the product is in gaseous state. So Kp will not be defined over here. We have only Kc and we will take only Kc into consideration. This was an important fact which I wanted to explain you through this example. Now I will take one more example and I will explain a bit more about it. Let's take this simple reaction, the aqueous medium. For this again now we can calculate Kc. Kc will be equal to how much? CH3COO minus. Since this is our aqueous phase and the hydronium ion concentration, this is the active mass of the products divided by the active mass of the concentration of the reactants, which is CH3COH active acid, acetic acid, multiplied by this we will take as unity, because the reaction is taking place in water and the concentration here will be taken as constant, because the concentration of water will not change, because it is the medium in which, it is the solvent in which the reaction is taking place. So this will be taken as unity. Okay. Now here also we see that there is no gaseous phase. So here also the Kp will not be defined over here. Not defined over here. Okay. So in this way we see that we have come to this conclusion that the active mass of the solids is always taken as constant. Moreover, the active mass of the liquids, if it is a solid, if it is a liquid and a gaseous equilibrium, then the active concentration of liquid is taken as unity. Second thing, and the third thing is that whenever none of the reactant or a product is in gaseous state, then Kp is not definable. So we come to these three conclusions. Now let's come over to the effect of mode of representation of value of Ku. This I will tell you now. Now I will tell you about the effect of mode of representation on the value of Ku, means how the value of equilibrium constant will change if we reverse the reaction, if we add two reactions, then how the value is going to change. Now let's consider a simple reaction A plus B forming CNT, a reversible reaction. Suppose the value of equilibrium constant is K into 1, and suppose if we reverse the reaction, if we do it like a C plus D forming A plus B, now the value of the equilibrium constant will be reversed. So the equilibrium constant value will be 1 by equilibrium constant of 1. Okay, the equilibrium constant 2 will be equal to how much? Equilibrium constant 1 upon A. This you can do from that formula also, the active masses of the reactants, because now the products are now the reactants. Okay, so the value will be reversed. Okay, suppose the value of this was 20. The value of equilibrium constant for this reaction was 20. Now the value of equilibrium constant will be 1 upon 20. Okay, got it. Now come on to another case in which we are seeing that this is our equation, and here the stoichiometry is double. Okay, the stoichiometry is double. So in this case, what will happen? Suppose this is the equilibrium constant. This is our equilibrium constant for this reaction. Then the equilibrium constant for this reaction will be how much? The equilibrium constant for this reaction is square of this. Okay. Suppose the equilibrium constant value for this reaction is 3. Then the equilibrium constant for this reaction will be how much? 3 square means 9. Okay. If the equilibrium constant for this reaction is 10, then the equilibrium constant for this reaction will be how much? 10 square means 100. Okay. Now let's come to another example. This as a general representation. Suppose the stoichiometry is changed n times, then the equilibrium constant for the new equilibrium constant for this, in which we have changed the stoichiometry n times, will be how much? The equilibrium constant raised to the power n. So these are some simple mode of representation. One more I would like to tell you here. Suppose you are having a reaction of this A forming B, and the equilibrium constant is given by 1. Equilibrium constant is 1. And suppose another reaction is C forming D. Okay. And here the equilibrium constant is given by 2. Then what will be the equilibrium constant? If you add up both the reactions, then what you get? A plus C, B plus D. So the equilibrium constant for this reaction will be how much? Equilibrium constant of 1 multiplied by the equilibrium constant of 2. If you are adding the reactions, then the equilibrium constant gets multiplied. And likewise, if you are subtracting two reactions, then the equilibrium constant will get divided. Okay. If you are carrying the subtraction process, then the equilibrium constant would have been KEQ divided by 1 divided by 2. Okay. Means the equilibrium constant will get divided in that case. Okay. Suppose it was K1 for this reaction, and if we were subtracting it, and it was suppose it was equal to the subtraction process over here, it would have been A minus C, B minus C, D. Then the equilibrium constant will be K into divided by K. Okay, so this was all about the mode of representation of the reactions, and in my next lecture I will be telling you about the relation between the Kp and the Kc. I will tell you about the relation between the Kp and Kc. Okay, thank you so much.